Hello and welcome to today's webinar. CAESES delivers shape optimization and works with Ansys CFD/EFEA to optimize turbomachinery designs with your presenter, Mattia Brenner, Head of Sales for Europe and North America at Friendship Systems. My name is Maria Ma, the Marketing Campaign Coordinator for Engineering.com, and I'll be your moderator today. First, a few housekeeping items to cover. Today's webinar will be recorded, then available for on-demand replay on engineering.com. For attending our full live session, you'll receive a PDH certificate within 48 hours. If you have any questions, please submit directly in this webinar interface, and we'll try to address all questions during Q&A. Now, without further ado, I'll pass it over to our presenter. Mattia, over to you.
Yeah, thanks, Maria. Thank you for the introduction and very warm welcome from my side as well to everyone joining us today, this afternoon or this evening, wherever you're located. What I would like to talk about today is about our tool CAESES and how CAESES can be used as a geometry engine to create a powerful combination with Ansys, specifically the Ansys Workbench and the tools that are available within to run design studies and shape optimization. And before we actually get started, I have a very short poll that I would like to launch here to get an idea of who's joining us today and maybe what kind of experience you bring along in that field. So it's just one question.
Thank you. Attendees, please let us know. Are you using automated design exploration or optimization? Yes, regularly. Yes, but you're just getting started, or no. We'll give you a moment to respond. Looks like we have 42% said no, 36% said yes, but just getting started, with 22% saying yes regularly. Thank you, attendees. Mattia, back to you.
Great, thank you for this feedback. I think we have a pretty good mix here of people that bring along more or less experience. And I think this webinar, the content will address everyone within the spectrum. So let's get started. The target of what we are doing with our tool CAESES at Friendship Systems is automation of the design process, or specifically automation of certain steps, at least, of the design process. And the reason is that due to laws and regulations, but also competition in the market, the demand for performance of engineering products is very high, and we feel that in many cases this can only be reached with optimization. And optimization, or let's say more broadly speaking, automated design exploration, can lead obviously to better and optimized design, but it can also shorten development times, reduce design cycles, and maybe a somewhat underrated point is that it can increase the knowledge about the product behavior in early design phases, basically by giving an understanding of which parameters are the drivers of the performance, and can give important information to guide design decisions later on in the process. And if we want to automate such a design process, we typically need a set of tools to fulfill different roles in this process. And first of all, we need a simulation tool or several simulation tools that can provide the performance information that we're interested in. So this gives us a feedback of how our design is performing. We will need a driver of the optimization process, which provides all this design of experiments or optimization strategies, gives us opportunity to look at the results, post-process them, and so on. And finally, we need a suitable CAD tool that is able to produce all the different geometry variants that we want to create throughout this process. And basically, this last point is what we focus on with our tool cases. So the next question might be, as you've just heard, cases, it's, let's say, the prime application of cases fulfills the role of being this suitable CAD tool in this process. So you might ask yourself, why do I need another CAD system? Typically, I guess every company nowadays is using some sort of CAD system to do mechanical design. And in our experience, most of the bottlenecks that people encounter when they're trying to set up or run a design exploration or optimization process are connected to the handling of the geometry. And these kind of bottlenecks can be that the geometry variation with a, let's call it, traditional CAD system is often tedious or prone to failure, which means that you might change certain parameter values by your optimization algorithm, and the geometry is not able to regenerate, or it regenerates with certain failures. And that, of course, is not something that works well during the optimization process. Another important point are constraints. So typically we have certain constraints that are connected to our design, and we would like to take these constraints into account when running the optimization, because at the end, the optimized design should fulfill these constraints and not be very well performing, but for example, be difficult to manufacture or not fill or not fit in a certain space constraint that we have for packaging. Another point is the quality of the CAD model. So the next step after we have generated the geometry variant would be to send it to our simulation tool. And typically the first step there is to create a mesh for the simulation. And we need to make sure that the geometry has a sufficient quality in order to be processed by the mesh generation right away. So often, at least for CFD computations, it needs to be watertight, or the level of detail needs to be at the right point for the kind of simulation we're running. Another point is the efficiency. So we want to have, of course, a very flexible variation of the geometry, but we don't want too many parameters, because typically the effort for optimization scales maybe even in a quadratic fashion with the number of parameters, and we would like to be flexible, but with as few parameters as possible, so that we can run an efficient optimization process. And finally, the kind of geometry that we are trying to optimize needs to be controlled. We want to control certain properties that are critical for the performance, and that's not always possible, let's say, in the way we would like to do it. And basically, these are the specific points that we're trying to address with our tool cases. So cases is not necessarily or not at all a general purpose CAD tool, but it is a very specialized CAD tool, highly specialized CAD tool, with a focus on the parametric modeling specifically of complex geometries. These are, if you look at the pictures at the right, these are often geometries that involve free-formed surfaces or other kinds of complex geometric features that are often not so easy to parameterize with traditional CAD systems. And we want to be able to parameterize them. That's one of our focus. And we would like to be able to vary them in a robust way so that we can create all the design variants that we want without failures to regenerate the model or any kind of geometry issues that we encounter along the way. I mentioned this point before. We would like to have when we parameterize these geometries, an efficient way of doing so that we have a high flexibility for variation, but with less parameters as would be needed maybe in other systems, or at least as few parameters as possible. And we want the geometry to be simulation ready, and we're able to provide a geometry that is automatically prepared to be used for the downstream meshing and simulation processes. And finally, in CAESES, we are able to monitor geometrical constraints, flag designs as feasible or infeasible, and we are also able to build some of the constraints directly into the model so that all the variants we generate automatically fulfill these constraints, which of course is a great gain in efficiency again in the optimization process. So this is a brief introduction about the tool that we're talking about, CAESES. And now I would like to go over to the CAESES app for the Ansys Workbench. So this whole development, let's say, of the app started with customers of ours who were users of Ansys Workbench, and they wanted to use CAESES within the Ansys Workbench. So typically they're using already several tools in the Workbench and have their existing workflows, or they even use the system to distribute and queue computations in their HPC environment. And these were the drivers for us to develop the CAESES Workbench app. And the workflow of the app that we developed and that we kind of envisioned before the development was that you would start the process within CAESES, so in the graphical user interface of CAESES, where you would set up your parametric model. And this includes the definition of all the parameters that you want to change, the geometry exports that you want to send out of CAESES later on. And once you have wrapped up all the setup, then you can move to the CAESES Workbench app. And there you will get a set of parameter values that is provided by the parameter set of the Workbench. This would launch CAESES in batch mode through the Workbench app, update our geometry model with the current set of parameters, export the geometry, and then the geometry is sent back to Workbench for meshing, solving, and then you can, of course, repeat the whole process in a manual or automated way and iterate through different designs. So at the current state, we actually have not only one CAESES Workbench app, but we have a set of different apps. And the first one that I want to mention here is what I would call the general purpose app that can be used with generic geometries. So basically, many of the geometries we've seen a few slides back where you would like to run a shape optimization. This connects to design modeler or space claims. So basically, as I shown before, CAESES exports the geometry and would then send it to design modeler or space claim, and then it can be transferred to the meshing. Then we have a more, let's say, dedicated app to Turbomachinery Applications, which is used to transfer blade geometries to TurboGrid. We have two different methods with which we can transfer this geometry. We can create sectional data for the blade and transfer those sectional blade data, or we can export the surface geometry of the blade and transfer that to TurboGrid. These are two options that might be suitable for different applications. I will say a little bit more later on. And as you can see here, also it will create multiple TurboGrid entities when you have detects multiple blade exports from one geometry set up as we see in the picture. And finally, we have this what I call interface app, which can be used to set up a connection between CAESES and the Workbench when you're running an optimization within CAESES. So we have also some kind of optimization environment within CAESES, and if a customer for some reason would like to do that, then this is also a way to transfer the geometry into the Workbench, which will run in batch mode in this case in the CAESES environment. So how does it work? How would you use these apps? First of all, you need CAESES, of course, the tool. So the app is not standalone, but as I mentioned before, the app is an interface between the Workbench and CAESES. So you would need the CAESES as an application running on your computer, and then you need the CAESES app, and you can get the CAESES app in the Ansys App Store, or all of the apps that I mentioned also come with the installation of CAESES, so you can also pull them from there and put it into your Workbench setup. So then the next step, as I said, is to prepare the project, set up your geometry parameterization within CAESES. And the crucial step here is then to define all the design variables in your project that you would like to be able to use for the later optimization, which you can see here. You can select certain parameters to be variables, and you can also specify bounds for each of these variables, lower and upper bound. And then another preparation step would be then to collect basically the geometry that you would like to transfer from CAESES to Workbench for downstream processing into a folder here in CAESES, and define the export format that you want to use to export the geometry. And here's just a side note, for the general purpose applications, at least, we typically use the SAT format for the geometry transfer, because it brings along certain properties that I will mention a bit more about later on. Of course, if you're using the TurboGrid app, you will use some dedicated formats for the export there that I will also talk more about later. So through the Workbench app, CAESES is run in batch mode, and it is controlled by a so-called FSC script file. This is a script file that contains the parameter data that we want to send to CAESES, and it also contains some commands for the geometry export. And there is no need for scripting or manual scripting if you're not interested in these kind of things, but this FSC file can be generated automatically for a project after you have done the settings that I talked about before. You specify your design variables, specify your exports, and then you can automatically generate this FSC file. And this FSC file is then loaded in the CAESES Workbench app through the context menu here. And now you have access to all of the parameters of the CAESES project through the parameter set in Workbench. And CAESES is fully integrated in the workflow, so you can connect now the geometry to all your other workflow components. And of course, you can control the parameters in the parameter set manually, or do so in an automated way using Design Explorer or other tools like OptiSlang to run a full-fledged automated optimization. Just a brief, a few words about the topic of geometry exchange. I mentioned that we recommend a specific format, SAT, for the geometry transfer of general purpose geometries. And the reason here is that we don't only want to transfer the geometry itself, but we also want to transfer a couple of other informations that helps the meshing process in Workbench. And typically this is the identification of certain boundaries of the geometry. So we want to specify certain patches of the surface geometry to get certain boundary conditions or certain mesh settings, and to identify the different regions of the geometry. In CAESES, we simply apply colors. So you can apply different colors to the different parts of your geometry, and you can use arbitrary names for these colors. So you can assign a color to a surface, as it has been done here, to this to the inlet surface of this duct. The actual color value doesn't matter, only that you have different colors. And what is important is the name of this color, which is then included in the geometry export. And when you import the geometry then in Workbench, in Measure, and so on, then you will get these boundary IDs as named select, so that you can address these parts of the geometry directly and automate the process of assigning different settings to the different parts of the geometry. Is quite a crucial step. That's why I'm mentioning it, in order to be able to have a repeatable process for different geometry variants that you want to compute in an automated way. Finally, just a few words about some possibilities that arise with these apps, apart from using the individual apps that I mentioned. So what is also possible is to combine different apps in one workflow. So here, for example, we have a combination of the general purpose app for volute casing, for a pump or a turbocharger, for example. And we have an instance of the TurboGrid app that is used to transfer the impeller blade geometry, and then they're meshed individually and combined in one CFX computation. Another possibility here, I think mostly what I've mentioned before was related to CFD. Of course, it's also possible to connect the geometry to a structural analysis, FEA. So here, for example, we have an case study that we did, which was an optimization of a mirror blank for an optical sensor, airborne optical sensor with the targets of high stiffness and low weight. And as you can see here, the geometry that is created in CAESES for this mirror blank with this hole pattern is transferred to a static structural analysis and modal analysis. And this was presented at the CADFEM Ansys conference. So in case you are interested in this, I can also provide more material. So specific topic of today was optimization of turbomachinery with the connection of CAESES and Ansys Workbench. And I would just like to start this specific topic with a few words about the turbomachinery design capabilities of CAESES. In terms of applications, we can cover all kinds of components and geometries that you might encounter in turbomachinery design. This can be impellers, like radial impellers, as you see here, or axial turbomachinery, like gas and steam turbines, but also other type of turbomachinery, like propellers for airplanes or for ships, fans, but also not bladed geometry like volute casings or exit casings, this exit casing for a gas turbine. And of course, combine things together and run or model, parametrize the whole assembly, like this hydro turbine that we see here, or pump with like this two-stage pump. So in general, in terms of design capabilities, we have comprehensive modeling capabilities for all kinds of rotors, stators, and casings. You can also add, let's say, more additional components, let's say. I don't know if they're more advanced. That was what I was going to say. Like end wall contouring. So if you have a non-axisymmetric hub, either on your radial impeller or on your axial machine, you can include that in the geometry parametrization. You can also include all kinds of other secondary flow structures, such as bypasses or wastegates on a volute casing or turbocharger in general. You can add cooling structures for blades, as we can see on the right in the upper right in the picture. Ported shrouds like this compressor in the middle with the animation, and so on. So it's not limited to blades, it's not limited to volutes, but everything that you have in terms of geometry in that region can be included. There are also possibilities to analyze imported geometries. If you have existing data in your database and that can be processed and can also be used for an automated fitting of a parametric model. And you can also integrate in the parametrization process fully customizable preliminary design methodology. So we're not a preliminary design system per se. So we don't bring along a whole library of preliminary design methods, but we have a very flexible coding environment, and we have set up already some methodologies, and this can also be done completely by the user or by us in cooperation with the user to include certain steps in the process. Here are just a few pictures, so you get an idea of the user interface of CAESES. This is obviously an impeller design. It's a turbine impeller or a pump impeller. And if we look specifically at blade modeling, we have, of course, complete parametric blade modeling capabilities for either radial, axial, mixed flow rotors. As I mentioned before, the important goal is to have a high robustness and flexibility of these parametric models for automated variation. There is a high level of customization, so there are no black box models where you can just fit in your parameter values, but all parametrizations can be completely created by the user from scratch. And we can fully integrate, of course, into existing workflows. There are a lot of capabilities to tune shape details that are connected to the blade, like their root fillets or scalloping of the impeller, leading edge shapes, blade tips, and many other things. Of course, we can include manufacturing constraints if you have certain manufacturing methods like milling, certain milling methods, flank milling, or versus other milling methods, or you have casting, at least in part. You can include all of these considerations into the parametrization to make sure that your geometry works with that manufacturing method. And yeah, we can use automated fitting procedures to match imported geometries. We can create solid or fluid domains and export them, as we see, for example, in the impeller at the lower left. And we support special or proprietary export formats like GeoMturbo or TurboGrid. So now I would like to show a small case study about the turbine stage. So what we have here is an axial turbine stage with 30 stator vanes and 59 rotor blades. The operating conditions here are 25,000 RPM, and we have a prescribed total pressure and temperature at the inlet and a prescribed static pressure at the outlet. And the objective is to, or the objectives are to maximize the isentropic efficiency as well as to maximize the power. Of course, the geometry was parametrized in CAESES, and I would just like to quickly explain the approach for at least many blade parametrizations that we use. We have a specific parametrization technology that we use for many complex freeform surfaces. And the idea here is that we make use of a building pattern. Here for the turbine blade, it's a airfoil section, and the airfoil section is defined as a pattern with all the parameters that are needed to create the actual shape, as you can see here. And then we define functions that describe how these parameter values change in the sweep direction of the surface. So for a blade, I think this is pretty straightforward. We have our airfoil section, and we want to sweep the blade in radial direction. And there we have these functions that describe how these parameters change in radial direction. And for every arbitrary radial position, we can get the exact parameter value from these functions. So if we combine this information, the building pattern, the distribution functions for the parameter values, then we can generate the surface. And this works, I think, for the concept is not foreign to many people who are working on blades, but the same concept is used for all kinds of geometries, like for example, a volute casing that I mentioned before. The cross section would be the cross section through the volute scroll, and the functions, the distribution functions for the parameter values describe how the parameters change in circumferential direction of the volute. So it's always the same approach, basically. So we can generate the blade surface, and in the following step, we then add details like the filleting at the blade root or tip, and so on. So here I have a quick overview of the parameters that we selected for the optimization. So the whole parametric model here has a few more parameters, but we made a selection of should be 14 parameters in total that we're using for the optimization. And the first set of parameters is related to the stator vane. And we have, first of all, the stagger angle. So all of these are global values. So it's not, let's say it's simple optimization approach here. We have a stagger angle distribution function for the spanwise or radial direction. And here we have just a parameter basically that there's a multiplier to this distribution function. That's why we have one global parameter for the stagger angle for the complete vane. And here you can see how the individual airfoil section would change. And here you see the complete blade. And maybe one thing to note here is that, as you can see, actually the chord length changes here when changing the stagger. The reason here is that we have fixed boundaries of the blade. So we have decided to fix the leading edge and the trailing edge stacking line, basically, and that which means if we change the stagger angle, we rotate the blade, then the chord length will change, in case you're wondering. So the next parameter is the leading edge radius. In this case, we have actually an elliptical leading edge. This is another parameter that was not used in the optimization that defines whether we have a circular or rather elliptical leading edge. So this is the next parameter. Then we have selected the leading edge wedge angle and the inlet blade angle. So that's the metal angle of the blade at the leading edge, as well as the same for the outlet or the trailing edge. And then we have the maximum theta value. So this is the maximum circumferential offset of the blade at the leading edge. Here you can see again this radial or span-wise distribution function of the theta value at the leading edge. And again, we're using a multiplier to let's say fully take this bow into account or not. And then we have finally a parameter that controls the shape of the leading edge stacking line. And then we have this basically the same set of parameters for the rotor blade as well. So I don't need to explain much. I'll just click through the animations so you get a feeling again how it influences the shape. Again, the leading edge wedge angle, the metal angle at the leading edge and at the trailing edge, and the max theta, the lean of the blade. In this case, we don't have this curved shape, but we have the maximum value at the shroud actually. And again, the shape of the stacking line at the leading edge. So this is our set of parameters that we selected for the optimization. We have set up our parametric model, and then for the geometry transfer, we use a custom export in CAESES to export the geometry to TurboGrid. And as I mentioned before, this can be done in either sectional data or surface geometry. In this case, we are actually using the surface geometry. One reason being that we were also taking into account the fillets at the root of the blade. And this is, let's say, more straightforward to do with the surface type geometry export. And these custom exports that we have in CAESES, these are really dedicated exports for TurboGrid, take care of all the necessary preparation steps to provide finally the files that can be interpreted without any problems within the optimization process by TurboGrid. So in case of the sectional export, of course, it will generate this sectional data there we have point data for each section as well as point data for hub and shroud contour. These will be generated within the export and then written into the according files. And for the surface geometry export, we're using actually the isim-tetin format to transfer the geometry. It also includes, apart from the surface geometry itself, boundary or feature curves that are needed to set up the blocking structure in TurboGrid, and these all of these let's say geometry objects will be identified automatically by this export and written into the files again accordingly. So once that has happened, all these curves and surfaces that come through the tetin file that we exported are imported in TurboGrid, and they are automatically assigned to their relevant locations by the CAESES Workbench app. So as you can see, we have the different curves, hub curve, pressure side, suction side, and so on, all the different boundaries and feature curves that identify these parts, and they are assigned to these topological entities. And then, of course, the user can adjust the mesh or layer topology properties in order to create the suitable mesh for his computation. In terms of the optimization setup here of this turbine case study, we have two TurboGrid instances that are connected to the CAESES TurboGrid app because we have two separate exports for the stator vane and the rotor blade, and they're solved together with CFX. So we have about 5 to 10 minutes computation time per variant, and we're running a design of experiments using Design Explorer, and you can see the setup here in this on the workflow setup on the side. So if we look at the results, we ran a DOE as mentioned using 268 designs with a Latin hypercube sampling, and you can already see there's a pretty nice Pareto distribution from the DOE alone. So we did not run any further optimization in this case study, but as you can see, the Pareto frontier is pretty well noticeable here. And if we look at some selected results, we can see that compared to the baseline, which is highlighted in dark red, some significant improvements were achieved both in terms of the isentropic efficiency as well as power with the optimized designs. If we just have a brief look at the correlations of the different geometry parameters to the objectives, which is usually interesting thing to take a look at, we can see that here the correlation or the objectives are very strongly dominated by two of the parameters, the same two parameters for rotor blade and stator vane, which are the outlet angle, so the metal angle at the trailing edge, and the stagger angles. These have the most pronounced influence on both of the objectives. And here is a quick look at the comparison of the geometries of the baseline design versus the optimized design. So the baseline design here is the transparent one, the light gray transparent geometry, and the optimized design, the first one of the selected one, is in green. And this is the second design that was selected. They have a similar performance, as you can see, not too far away, but you can also see here that they have quite different geometry. So if I switch back and forth again, especially the bow of the stator vane here is quite different. Sorry. Finally, to conclude this case study, I have just a little bit of a side track here because I think it's an interesting topic that I wanted to mention. Is here we selected 14 design variables for the optimization out of the all of the available parameters in this parametric model, which can be quite a few more, can be 30 parameters, can be 40, depends on the parameterization. And already the 14 that we selected is not necessarily a small number. So sometimes the question arises, you want to cover as much ground as possible, look at the widest possible design space, but without going through the whole effort of doing an optimization with maybe 40 or 50 parameters. And we have a supplementary tool in CAESES for the task of the dimensionality reduction of the design space. So you have a large design space of 50 or maybe even just 20 variables, and you would like to keep the flexibility but reduce it to a smaller number. And what we use for that is a dimensionality or design space dimensionality reduction approach based on principal component analysis. So basically, we map our geometry data from the original space of a certain number of variables, here p variables, to a new space of p variables that we call principal parameters that are uncorrelated over the data set. So it removes, first of all the correlations between the variables that might have been there before. This usually happens that you have design variables that maybe influence certain areas of the geometry in a similar way. So they are somehow correlated. And the approach here with the principal component analysis works basically in a similar way like eigenvalue analysis. So you create a large variation of the geometry. You run a DOE with just the geometry variation, no computations, which gives you a large spectrum of design variants that you can create. And then you analyze the differences between all of these variants and basically extract the eigen modes or principal components. And then you can use these principal components, or we call them then principal parameters, as new parameters to control the geometry. And you can see here that we have a plot here that gives the percentage of variance that we capture with a certain number of principal parameters. And you can see that with one parameter of these principal parameters, of this new set of parameters, we can already reach almost 80% of the variance of the previous design space. And gradually, if we add more of these principal parameters, we approach 100% variance. And this gives us the possibility to optimize in this new design space of the principal parameters. And what we just need is the back transformation so that we create a certain set of values for the principal parameters of the number of principal parameters we select. So for example, here we want to use 4 of them, which gives us probably a bit above 95% of variance of the original model. And the optimizer sets values for these 4 principal parameters, and then we transform it back into the original design space by basically determining the parameter values of the original parameters and get the right geometry. And this is a very efficient way of reducing or very massively reducing the dimensionality of the design space. And here I just have to give you an idea of how these principal parameters act. We have the first one, which acts on the stator vane, which gives us 77% already of the previous design space. And you can see here where the influence is strongest. As I said, it's very similar to eigenmodes, like you have a certain oscillation that might happen here, especially along the trailing edge. We have the second principal parameter, which acts on the rotor blade, which leads us to 86% of variability. And again, if we add more of these principal parameters, we reach values above 95%, which is usually enough to cover a lot of ground of the original very large design space. So much for this case study, and also for the other things. I want to come now to the conclusions of my presentation. So as you can see, cases can be integrated in Ansys Workbench to augment its capabilities in terms of robust and automated variation of complex geometries. There are different apps available, including specifically a dedicated solution here for turbomachinery geometries that are meshed in TurboGrid. CAESES offers flexible and powerful parameterization capabilities for turbomachinery, but also other types of geometries. And this approach has been well proven on several different applications, including, of course, the axial turbine stage case study that I just demonstrated before. So this concludes my presentation. I think now we have some time left for Q&A.
Great, thank you, Mattia. And also joining us to answer questions is Michael Tooley, Senior Product Manager of the Physics Business Unit, and Bill Holmes, Principal Application Engineer from Ansys. Our first question is, how would such parametrized CAD tools facilitate 2D drafting for generating production drawings?
I think we have, of course, the capability to generate 2D parametrizations, but our approach is very much focused on the generation of 3D geometries that are then used for simulation. Basically, what we do in terms of 2D is mostly limited to what I've shown before of defining parametric cross sections for the surfaces that we want to generate, such as the airfoil section of the blade we saw. You can create this or set up this geometry in 2D, define your parameters, and then of course the goal is to generate a 3D shape that we want to use then for the optimization task. It's but it's not. I think the question was also part of. It said something about production drawings, right?
Yes.
Yeah. So this is what might come afterwards. That you want to take your optimized geometry and then create production drawings for it. That is possible in a certain amount in cases, but that's not the focus. I mean, the typical approach by our customers would be to create an optimized geometry and then move it to a downstream CAD system for potential further work on it, and then generation of production drawings.
Great,
this is not the main domain of CAESES.
Thank you. Next question. Do you have case studies of ship hull geometry, parametrization, and further hydrodynamic optimization?
Yes, very many. in fact, we our company originates from that field. We initially were solely focused on ship hull parametrization and ship hull optimization, and then we, over the last probably 10 years or so, step by step, we also moved into other fields of application. So yeah, we are very strongly rooted in the maritime applications, and we have a lot of users worldwide who uses CAESES specifically for these tasks, and we are also able to provide many case studies if requested about that.
Awesome, thank you.
And can be ship hulls, maybe just, but also other hydrodynamic optimizations connected to ships, like appendages, propellers, things like that.
Awesome, thank you. And actually, a follow-up question to that, is it possible to optimize propeller geometry at the same time with the ship's hull?
Yes, sure. As long as you have the simulation in place that covers this ground, so you have a simulation of the flow around the ship hull, which either involves the propeller directly within one simulation, or you have coupled simulations for the propeller and the ship hull. But as long as the simulation part is covered, that's no problem for us. We can combine the parametrizations of the ship hull and the propeller and involve both of these things at the same time in one optimization task.
Great, thank you. Next question, is there a possibility of modeling scaling factors applying Buckingham pi for dimensionless verification between small scale prototype versus full size?
I'm not 100% sure if I can answer that question, but I mean, I think I would say yes, but I'm not 100% sure how to answer that in detail. But I know at least that people have done optimization, and again, that's something that I'm aware of from the marine field, that optimizations are often run for model scale computations because of the high Reynolds number of the full scale, and then yeah, translation factors, so to say, can be taken into account for scaling the model scale results to full scale results.
Great, thank you. Next question, can you go from cases direct to 3D printing?
Yes, sure, you can do that. So we can export STL files, for example, in several different flavors, and I think that's usually a good input for 3D printing. I think this is definitely an interesting field that we are working or just starting to work on more intensively. That's also related to the field of turbomachinery. We were just starting a R&D project with Siemens here in Germany that is focused on additive manufacturing, and we also, within this project, we want to actually develop dedicated tools also for this applications. So for example, that if you generate a geometry in CAESES, or you're optimizing a geometry in CAESES, but also in other tools like Siemens NX, that you can check the geometry for constraints related to the manufacturing method, for printing, or create support structures, things like that.
Great, thank you. Next question, how much time will it take to optimize a given hull form?
If it says hull form, I guess that's also again relating to ships. I mean, this is I think it's a difficult question to answer in a generic way, because it very much depends on different factors. It depends, of course, on the number of parameters that you involve in the optimization. So the larger design spaces you have, as I mentioned before, the more time will be needed. But it also depends on the simulation side. So if you have simulations that are more expensive, or if you're optimizing for a combination of different design points, you're doing a multi-objective optimization for, and you have to run simulations for different operating conditions or design points. That all, let's say, increases the time needed for the optimization, and that's why it really depends quite a lot. It can be done maybe in a simple case overnight or over the weekend, but it can also take maybe a few weeks if you have very expensive computations and large design space.
Thank you. Next question. What programming languages are used and what is involved in tying to/from another modeling program?
I mean, you don't really need a let's say a lot of programming language when using cases. There are certain things that can be scripted outside of cases. I mentioned already these batch scripts that run cases in batch mode. These, in many cases, can be created automatically, as here for the connection, but they usually don't need many commands. And we have also an internal scripting in cases, which we call feature programming, which uses kind of an own language. Might be loosely based on C++, but it doesn't really need programming experience, or at least not much in most cases, because again, these feature programs that inside cases can in parts be generated automatically. There is a lot of help, auto-completion support for users that are new to the process. So there is not really any, let's say, named programming language involved in using cases or connecting it to other tools.
Thank you. One more question. Can the same approach be applied to wind turbine blade design optimization?
Yes, sure. Yes, of course. Basically we can generate all types of geometry in cases, as I tried to show in maybe some of the collection of pictures that I had here. And we can, of course, also generate wind turbine blades, and we have also customers who do so or have done so, and that's no problem. Yeah.
Awesome, thank you. That's all the time we have for now for questions.
That's great. So I would also like to thank all the attendees from my side. And just a final remark before everyone is leaving. If you're interested in what you saw today, then of course you can get in touch with us. You can also download the trial version of Cases on our website, www.cases.com. And you will get, by registering, you get automatically a trial license. And of course, if you want to specifically test the connection of cases with Ansys Workbench, we can also provide examples of parametric models so that you can test it directly within Workbench without having to actually work on cases itself. So, and yeah, there's just one more remark. I don't know if Maria, you were going to mention it. We also have a small survey at the end, so takes just 1 minute, I think. So of course, I would be happy to get some feedback from the small survey if you can take the time. So,
great.
Thank you.
Thank you, Mattia, for providing a great presentation and great value today. And thank you, attendees, for joining us. We hope you'll return for future webinars. Bye for now.